CNT120, Chapter 6, we are on the section on our wireless standards. Remember, wireless LANs work at layer 1 and 2 of the OSI model. Again, layer 3 and above, IP, TCP, UDP, all that is the same for wired and wireless. So when we talk our wireless standards, we're really looking at the layer 1 and 2. And I just remind you here about, layer 3 and above, we're using IP, TCP, UDP, all the good stuff. It doesn't matter the operating system you're using, Windows, Apple's, Linux, it does not matter. These standards are ensuring that the wired and wireless communications can integrate on the same network and not have to have some sort of translation. These can actually integrate and work with each other on the same network. So our wireless standards 802.11, here is all the substandards over the years. I have it broken on a chart here in a little bit, just trying to remind you, and even some of the symbols that have been used over the years to denote what type of wireless standard this network card is, this wireless device, this access point, whatever it happens to be, letting you know what standard it is. If we look at our OSI model, okay, application, presentation, transport network, data link, physical. When we look at our wireless standards, again, they're looking at the bottom two layers, and more specifically, the data link layer is broken into two layers. There's the logical link control sublayer and the media access control sublayer. So your data link layer is broken into two pieces. The upper half, the logical link control, handles multiplexing, flow and error control, reliability, those sorts of things. The bottom sublayer, media access control, that's where your MAC address, okay? Media access control, this is the part that's actually getting the data onto either the wire or our radio frequency going out through the air. That's this part right here. So a lot of what we're looking at is really focusing on this bottom layer and like this kind of like this second, the bottom sublayer of the data link layer. 802.11 standards vary at the physical layer. 802.11 and later modify the way frames are used at the MAC sublayer. Okay, that's something they mentioned in there just to remind you. Here is our standards over the years. I tried to put it on one chart here for you that you could even like save this. It's pretty much the same thing that was in the book, but I just kind of reproduced it here so you could save this for your notes if you wanted to. I even put the year in here just to kind of give you a ballpark time frame of when these things were developed. For the longest time, we just referred to them as 11B, 11A, so forth, and eventually they started going by Wi-Fi 1, Wi-Fi 2, so forth. Right around this time frame, I think, is when they really started to brand that and call people to that attention. I think the idea was to make it a little easier for people to understand the progression, or this is Wi-Fi 6 compatible, this is Wi-Fi 7 compatible, and so forth. But back in time, 802.11b, this was 99 time frame, 2.4 gigahertz band, 11 meg throughput, about 100 meters. And again, in these days down here, you might be rated at 11 meg, but with the unreliable nature of wireless, you would be lucky if you got half that. Things have progressed tremendously, and you're getting a lot more of the full bandwidth, if you will. 11A was developed next, 99 ballpark, 5 gigahertz range, 54 meg, 50 meters. 11G, for a lot of people, we used 11G for a long time. 2003 time frame, 2.4 gigahertz band, 54 meg, 100 meters. And then 11N, 2009 time frame. Now we have two different frequency bands to use. 600 meg throughput, indoor 70 meters, outdoor 250 meters. 802.11ac, 802.11ax, 11.2be. So just be familiar with what these are and be able to, if they give you some specs here, know that this is 11ac or Wi-Fi 5. If they give you some specs here, know that this is 11ax or Wi-Fi 6. I think they even put a note in the book about that. If you're doing the certification exam, make sure you know this well enough that I'm going to say you can match these up or identify them. Back to our OSI model layer, the bottom sublayer of the data link layer, the MAC sublayer, manages our MAC address and access to the media, placing the frames on the media. So now they're going to talk about our frames, our wireless frames as opposed to our wired Ethernet frames. So our wireless is going to add some overhead because it needs a couple more frame fields to get the job done. So because we're adding a couple more frame fields to get the job done, there's more overhead. There's more packing material, if you will. The box is bigger, if you will. So it's adding some more overhead to the network because of that. There is a couple different frame types that you're going to run into: management, control, and data. The management frames are used for associating and reassociation, the probes and beacons. When you boot up your laptop and start looking for an access point to connect to, these are some of the management frames that are moving around to find that access point and actually start associating with it. The control frames, these are the ones that are actually kind of controlling the way, or getting the data, starting to get the data on the network, if you will. So the acknowledgments, as well as the request to send, clear to send frames, that's what these are, trying to get onto the network. Then there's actual data frames, the ones that are actually carrying my data, whether it be a file or whatever, my email or whatever I'm trying to send. Here's the comparison of our Ethernet typical frame and then our wireless frame fields. Thinking back to when we look at Ethernet frame field before: preamble, destination address, source address, type, and then data. Well, with a wireless network, we need a couple additional fields. We have that frame control field. We have address 1, 2, 3, and 4. Well, before we had source and destination, but now we need address 3 and 4, if you will, because we have access points in the middle. So we need a way to get it to the access point and then off, either onto the network or to that device. So there's additional address fields, and then a sequence control as well. This for acknowledgments and that sort of things. That's what we're seeing there. Here's your frame control field, and how large a packet is fragmented. I apologize. So your frame control protocol in use, type of frame transmitted if fragmented, the address field, source address, transmitter address, receiver address, and then destination address. These are the part in the middle, the transmitter, and then the sequence control field, how a large packet is fragmented. So if we do fragmenting, how that is fragmented, if you will. And then here's a breakdown of all those fields if you want to look at some additional details here. So with our wireless network, we want to talk how we're getting the signal onto the network. So with our wired devices, we have a medium that we can send our data onto and get it off. With wireless, we don't have that medium. It's a little bit more of a free-for-all. So what ends up getting used is what's called CSMA-CA. Well, let's come back to that. So we want to remember kind of how we got started and kind of how we evolved. So if we go back to the early Ethernet, we're talking coax bus Ethernet days, the access method that got used here was CSMA-CD. Carrier sense multiple access with collision detect. So back in the wired coax days, if you will, coax bus days, when you went to send data, you would listen for traffic. If you heard any traffic on the network, if there was electrical signals moving by, you waited. You waited for that transmission to get done. Once that transmission was done, you sent. There was no waiting here. There was no double checking. You just literally sent your data. And hopefully you would not have a collision. You and somebody else would not send at the same time and collide your two data frames together. If you did not, if you happened to send it and not collide with anybody, awesome, your message got there. It's assumed that it got there. There's no double check. But if you sent at the same time another computer did, and those two signals come together on a wire, it's like almost like two cars hitting. You hear the crunch, if you will. Here you have that electrical spike of all those signals kind of like colliding into each other. Well, that electrical spike everybody hears and goes, oh, collision. And what would happen is, all right, I hear the collision. We're going to stop. We're going to wait. We're going to back off and then start this process all over again. So I listen for no traffic. When there is none, send. If I don't hear anything, hey, it got there, awesome. If I hear a collision, all right, let's start over, try it again. That is how your early Ethernet networks worked. Well, if I try to apply that to today, and I think they have that down here, there's no way to really kind of like control what's going on. It's hard to know that somebody else is transmitting or not. And I use this example. Think about in a large let's think about a large gymnasium or something. You have your laptop over along one wall, your friend has their laptop over on the far wall, and you're both connecting the access point in the middle. Well, your laptops are so far apart, my laptop would not hear your laptop and vice versa. So if we both go to send at the same time, I have no idea you're sending, you have no idea I'm sending, we would both send and probably collide. So in a wireless network, there's no way to be sure that there's somebody not on the far side of the access point trying to send when I try to send. That's called the hidden node problem. I think they might have alluded to that in the chapter you read. So because of that scenario with wireless networks, they use the CSMA-CA, collision avoidance. They're going to try to avoid the collision. So what happens now is, again, think about us sitting in a large gymnasium. I'm on one wall, you're on the other far wall with our laptops. When I go to send, I'm not going to hear you, so I won't hear your traffic. But what I'll do is I'll wait just a little bit. In case you were sending, you're probably done, and then I will transmit. And vice versa. If you go to send, you're like, I don't hear anything, I'll wait a little bit, they're probably done by now I'll send. And the idea is you're trying to avoid that potential collision. Here's an additional difference though. After I listen, I don't hear you, I wait a little bit, and then I send. Once I send, I literally wait for an acknowledgement from my receiver. And if I get the acknowledgement, awesome, I know it got there. If not, I'm going to assume something happens and I start all over. No traffic, wait a little bit. Okay, now I'll send. I'm going to listen for acknowledgement. I got one, cool, it got through. That is how the wired to wireless got adapted to try to avoid two people in opposite locations sending and having a collision, this collision avoidance, if you will. So when they talk CSMA-CA, that's what they're really getting at. There is also a request to send, clear to send option some of your access points can do. In this case, you actually, you're going to check to make sure no traffic. If there is, I'll wait. When there is none, I'm going to send a little note out to the access point. Hey, can I send? And the access point, if there's traffic, it's like, hold on. Okay, now there's no traffic. Okay, go ahead. And they'll send me a clear to send, and then I can send my data. Away I go. So it's a way to kind of avoid the collision, but having the access point play your traffic control, if you will. Again, that's going to add a little overhead, but you're a lot less resending because I'm not having the collisions and having to resend. That is an option that can get kicked in on our access points. All right, we'll come back in the next one and talk about association and all those kind of good things.